Okay, welcome everyone to these two parts of the lecture. I was not really aware what your background knowledge is, so at any point, if you want to speed up or want more details or anything like that, just pinpoint me or ask questions either now or later. This is why I provided the email address. And you can then also download these slides. I will prepare a link that can be just downloaded so you can make use of them. What is the background that we do in Vienna? Just maybe in a nutshell for myself, we are the mobile communication group, which is hosted at the Institute of Telecommunications. We do basically three major things. We do, on one hand, system simulators, which is open source and you can download it. It's a MATLAB simulator for LTE, LTE Advanced, and now 5G. We do the MIMO testbed, which you see in kind of results here, or the turning wheel for high-speed measurements. So we try to benchmark our simulators with these. And finally, where I come from, we do benchmarking of mobile networks. So we try to understand IP layer performances, optimize it, understand the impact of mobility, or also cell edge coverage. So how much data rate do you get at the cell edge? It's a very new topic which comes basically from smart meters and how well present are you in deep indoor coverage, for example. Anyway, what do we do today? What I want to show you basically is the basic operations of mobile networks. I would like to start with the core network elements and also introduce then some basic procedures. I will start very, very basic with GSM, move on to UMTS, and finally end in LTE. Now you might ask, why do you start in GSM or whatever, Stone Age technologies? But actually it's interesting that in the recent, let's say, 5 years, GSM has gotten more and more prominent again because all the smart meters are basically GSM-driven small devices that need also optimizations in these systems. What is the motivation in itself? Well, obviously the data volume is increasing every day, so we get more and more volume that we want to transport in a more efficient way, especially given that the resources are shared and pretty expensive. I mean, at least in Austria and in Germany. I don't know if it was here also such a mess basically in the sales of the spectra itself. And we want to achieve that at a given quality of service basically. So we would like to have a better understanding how the quality of service can be offered for different data rates and bandwidth needs basically. So how would it look like in the internet? Well, you all know the OSI model, obviously. So you would start with an application layer and then you would go down step by step to end up in the physical layer. And your counterpart, which would be maybe the server in the internet, would be capable to communicate between these different layers. What I want to introduce to you today is basically that this is what you use to communicate in the internet. And if you use a mobile network, basically you will have underlying a second set of network that hides every kind of mobility, interaction, and things like that. So basically, also a short teaser for today would be the different levels where we are interacting, because we will touch a bit on that. If you go from the top layer that you see, that is basically when you communicate between a server and your mobile client. For example, here I have an FTP, an HTTP, and an email session, which will be inside a PDP context. This is typically how you transfer data. So you create a context, you maintain that context, which provides you mobility, IP connectivity, and a certain kind of quality of service. And within that, you are able to run your service. Like in this example, the website that you transfer, which will be TCP streams, or if it's a wireless application protocol, might even be UDP in this case. While we get more simpler in understanding, if we go down, the information will be hidden if we go up. Because if we go up, we will understand, was it an email, was it a web page, was it a web page with a video streaming, or what was the content in itself. So basically the outline will be, we start with a short evolution. We will go 3G basically hierarchy, because basically it's a subset, or GSM will be a subset of that. We go through the core network elements. We will have a look at the basic hierarchy in the protocols and the procedures itself. Yeah, and we will have obviously in the end the journey of a packet from a mobile through the core network itself. Where does this all come from? Well, I guess you're familiar with it, but in case not, just to synchronize everyone, we have the 3GPP specifications. They are parted into reports and specifications. A report is typically when you want to research on something. So if partners come together and they do a study about if you should use external antennas or internal antennas and all these details that you will find in technical reports. The specifications itself will then be really what you have to follow or these guidelines. The numbering scheme is pretty easy, so either you go for the 20, where you will be in 3G, or later, which will be LTE, or you have something with 40, that would be the GSM parts. Typically, they have corresponding specifications itself. Let's see if that would work. No, sorry. I had a link to a specification just to show you. Only I think there was the release 13 changes. It's like 800 pages of a lot of difficult to understand technical blah blah. So I would rather advise you to go for a book, read the details that you need, and then dig into the standard in the place that you need it itself. So these standards are very wide. They are very detailed and very open, basically, so you can really implement everything that you need. However, they are pretty lengthy and also wide and broad. So, how does network architecture typically look like in a mobile network? Well, we can boil it down to 3 elements. We have the user equipment itself, we have the radio access network, and we have the core network. And then, obviously, everything that we connect to, like internet, for example, or a phone network itself. The elements that we describe would be, for example, your mobile phone would be the mobile station that contains a SIM card. So you have the possibility to use different devices like that. The radio access would be typically the base station or the radio network controller like you find it in UMTS. And the core network would be everything that takes care about home subscriber, for example, or your mobility management entity, or anything like filtering or gateways, or in my case, for example, roaming. So things like that. If we start very basic, if we start in GSM, we have basically just voice as a service, and the service itself was offered in time slots. So we had basically these 8 time slots. They would fit and be able that in one cell you're able to serve 8 different users. Next upgrade was basically then GPRS. Let's be a bit quick in the generations, where we have changed and upgraded in such a way that we are able to send data itself. So GPRS was the first time that we could, even so GSM was basically a digital system, it didn't support any direct digital communications. So GPRS was the first element where you could transmit data itself. So you could combine time slots and transmit data itself. And then we basically, with release 99, had UMTS. UMTS was the first evolution that was changing the system quite largely, because we started to introduce a packet-switched core. So in GSM, we basically slowly introduced GPRS, but the packet-switched itself was not a definition itself. So now we had a voice world and a packet-switched world, and we could transmit our data due to our needs itself. So that was the first element of flexibility. Then we also changed the radio access network, so we were capable of having soft handovers, we were capable of having no hard handovers anymore. That's one of the things we will come also today. If you think back about this first introduction picture I showed you, when you go with a mobile in a mobility scenario, I guess every one of you has had a tube ride here, also in London. If you move from one base station to another, what is very likely to happen is your streaming will fail, or your download will fail, or something like that. What happens is basically that your data has arrived to a base station you are not anymore. And the system itself needs some time to find you again. Some systems are a bit smarter or faster. Some systems take more time. So typical thing, we will arrive then in LTE. We see that the base stations are already connected, so the time that it needs to forward data from A to B is actually very small. So basically, what we have arrived to in the end would be then something where we have LTE. where we have migrated from something in the beginning that was voice only to something in the end that is packet switched only. In fact, if we go then for the LTE core, we will find out there is actually no voice implementation in the LTE core itself. VoLTE, as it's called, so voice over LTE, is basically packet switched voice over IP transmissions. So we have dropped actually the feature of voice communications completely. How could that look like? That is maybe a bit scary in the beginning, but don't worry, we'll go step by step through all the elements. On the upper left part where you... Sorry for my... Okay, then I will use maybe the mouse. It's okay. Can you see that? Yeah, I guess so. I just used the mouse cursor. Or does it do? No, I didn't see. I just used the mouse. Okay, so in the upper left corner, we basically have our GPRS system. What is the difference, or what is the unique element that we have here? We have basically a base station controller, and the base station controller will be connected, or the transmission system will be connected to a controller itself. This is GSM. The adding for GPRS was that we have a packet control unit, which allows us to connect to a core network packet switched. So we have here on the right top then the core network for all the voice parts. So all the voice calls will go here, and all the packets will go there. So basically everything that is packet switched will run through something we call the SGSN, so the serving GPRS support node, and going through the gateway itself to the internet. So we already see we have actually two major components. We have the radio access, which was this part. So everything to the left is radio access, and everything to the right is basically core network itself. And in the core network we have the voice and the packet switched core network itself. What is now different if we go for the next generation, so if we go for UMTS, we see that we already here have a connection between the radio network controllers. If you compare here the base station controllers, then if you would like to go from one cell to the next, you would actually need to forward a packet through the SGSN. So you need to go one layer higher up to the core network, and the SGSN has to find you in the next cell. Not so difficult, but still it has to reroute your packets from this PCU to the next one. That you could also easily observe yourself. If you want to try and make this example, you can go to 2G and have a look at handover times. You will see that it needs 1 to 2 seconds until a packet will arrive if you have arrived in a new base station or in a new cell. In UMTS, we have actually already a connection to the RNC. So the node B is already connected to the RNC, and the RNCs itself are intermeshed, which means that packets can be easily forwarded. So in 3G, the handover time between two cells is already at least an order of magnitude smaller. So there are 200 milliseconds, for example. So we have already a reduced connection time in these. And if we then go in the next lecture for LTE, we see that even the base stations are nowadays connected. So you have actually a very fast handover possibility. Now what's all that about? Well, basically, these are all the elements that will take care about security and all the other informations that you need. For example, your home location register, which will contain your profile, if you have credit or not, if you are able to attach to the network or not, if you are visiting, for example, like most likely I am in that case, or if your equipment is a problem of fraud or something like that. So it's mainly a database system that does all the operation and maintenance in these cases. In the end, what all of that is hiding your mobility. So the core point of these elements is that any packet that would go in here, or any phone call that goes in here, uses all of that to find you. So in fact, if that would work nicely, I can establish my PDP context, and I can travel to another country, I can travel to another base station. All of that is basically hidden in this network itself. So it basically hides all the kind of mobility that could occur. So yeah, this is basically just a short wrap-up on these. We had the three elements. We had, on one hand, the user equipment, so this user element. We have the radio access network, and we have the core network. So these are the three main ingredients that we are working with. We have started off in GSM at the digital connection for voice only, so circuit switched basically, and we have ended in LTE, packet switched only. So there we have only packets to be transmitted in the end. What are these elements now? I shortly pass by. Well, one of the simplest elements would be the mobile switching center, which basically takes care about anything that is related to voice calls. So on one hand, it has to do with the mobility management, which would be nothing else than finding your mobile. So it takes care about alarming your mobile, for example. So it will take care that it says, okay, your mobile seems to be in that kind of routing area. I have to alarm these amount of cells. And then boiling down to these different numbers of cells. Why is that interesting? Well, we will come later to the protocols that are behind that. Because that is basically one of the trade-offs that you see nowadays when you have machine-to-machine communications. You would like to avoid that you call all the smart meters in a capital city on a large scale, because a routing area typically contains a lot of cells. And if you have to ring up 1 million smart meters, that might put quite a load into your network that you would like to avoid. So a lot of the improvements we will see later for the newer releases are down to the fact that you would like to still have the mobility and the flexibility to find a user, but not at the cost of ringing up, for example, the whole of Vienna. So you would like to reduce or to have a balance in mobility and localization, basically. Why do we have this mobility management? Well, we have talked about we have a shared media, so we cannot keep users connected. We have to detach them from time. And we also don't have a control if that is turned on or off. So we have to track this. So basically, these elements are one of the elements that have quite a lot of processing power and a lot of storage that they need to keep track of all the users. Well, obviously, on one end, it's connected to the gateway, which is your gateway to, in that case, the phone system. And on the other side, it is connected to the radio network controller. So the box that basically does all the physical access. The counterpart to that would be the SGSN, so the serving GPRS support node. This is the box that basically takes care about the same for any kind of packet connection. So it does the mobility management, cell updates, for example, if you're moving, or routing area updates if you're not moving at all. I mean, for sure you have already had your phone beside a radio or something like that, and after 15 minutes you hear this dong, 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 dong in the radio. This is nothing else than a routing area update. So the SGSN is triggering the RNC and says, well, these are the users I have seen 15 minutes ago. Would you be so kind and check if they are still present? Can I really connect to them or not? Handling of data sessions, obviously. What does that mean? Well, in fact, if you want to hide mobility, this end doesn't know the link speed of that side. Sure, we have TCP on top, but that would be way too slow to act to radio activities or drop packets or things like that. So the SGSN also has to take care about buffering, for example. And in fact, if you would transfer IP packets, for example, and you measure delay, you will see that the SGSN typically can store 1 to 10 megabytes per user session. So you have also effects of interacting with your flows and the data itself. So this is what basically falls into caching. Either the subscriber data, like your home location register informations, or the data itself that the user has. Why would it take place here? Well, we will see later that in order to provide you the mobility, the mobile system has to repack your payload. So while we are talking about IP packets here, and we are talking about IP packets here, they are not the same. The GGSN will basically encapsulate all your data traffic into a new format. We talked about these PDP contexts, and then transmit these information through the network, which will hopefully end up at your phone. But between here and here, the IP that you had requested from a server and the internet is not visible to the devices itself. So you need something in the middle that basically is capable of unpacking and repacking these informations. The border, or the gateway GPRS supporting node as it's called, so the GGSN, is nothing else than a big routing device. So it basically has to keep track of the IP address on the outside as a gatekeeper, like a firewall, and your PDP context number on the inside, so your unique identifier of the mobile. And it has to juggle actually the packets that are incoming, repack them, understand charging and things like that. So basically it's the one that is triggering all the charging information, for example. So if you're ever interested in monitoring user traffic, that would be the place you can go, because there is all the charging going on. And it has basically to do the encapsulation in the GPRS tunneling protocol, which we will see actually in many flavors today. It also is responsible for quality of service. As said, this is the last place where you can easily access the user data. So if you want to apply quality of service, this is the place where you can still do it. So you can, for example, identify streaming, voice calls. If your Skype doesn't work in, what was it, Vodafone network, that's the place where it's done, because that's the last place they can basically detect IP packets or things like that. So this is actually, let's say, in this, nothing else than a firewall that you would have in a company, basically. More complex, admittingly, but not more than that. What is a bit more tricky and, let's say, basic functionality would be the home location register. This is the database that holds all the informations like your telephone number, your subscriber number, security things. So the key, basically you have one key on your SIM card, you have the counterpart in this home location register. This is the way how your phone can register to the network. The quality of service parameters, so which kind of tariff have you paid for, which data rate did you get, which service will you receive. This is one of the reasons, for example, if I would do a speed test here, or actually in fact I did, I get 20 megabits per second. If I do it at home, I get 2 megabits per second, because in the roaming case it's not properly transmitted, obviously. So these are all the informations that are stored in a home location register itself. That is also the place where you would change your telephone number. So if you are going to another operator, if you're migrating to another operator, you will change your SIM card, which would be basically IMSI, and assign, for example, a new mobile phone number in this case. So let's summarize shortly. We had, in the circuit switch part, we had this mobile switching center, and we had the gateway. The counterpart was the SGSN and the gateway for that. So we have these two packet switched elements. And in operations and maintenance, we have basically looked in detail into the home location register. These are like the core elements. There are obviously also others like the visitors or the equipment register, but that would be the core elements we will deal today, and also the core elements in this structure itself. How many people know that already and it's simple and we should go faster? Just put your hands up, at least. Was it too fast or too slow? You look so doubtful. It's okay? No, I'm just asking. Stop me in case. The idea behind that and to introduce these elements is to give you also then an understanding how they would interact. There is something called buffer bloat. How many of you know that? I guess many. Or no? Maybe? Yeah, same. Buffer bloating basically indicates if you download something from the internet, TCP for example, and it arrives here, then let's assume, let's say it's a great operator, has 40 gigabit connection to the GGSN. However, the GGSN is only connected with, let's say, 10 gigabit to the SGSN, and then the RNC is, let's say, somewhere far remote, 1 gigabit or something, and stuff like that. So we have said it has to be buffered somewhere. So we will have a first buffer here that accommodates for the fact that the link speeds are not the same. Arrives pretty quickly, and then he has to look for you, he has to alarm your mobile, and things like that. So we will have a first buffer stage here. We will then have a second buffer stage in the SGSN, which has to take care about encrypting your traffic, preparing it for the RNC. The RNC is actually a pretty small box, so he cannot be overfed because he will lose packets, and he will also signal back and say, oh, my radio link is really bad, stop it please. So therefore you will have a second buffer stage in here. And you will basically then have a very small buffer in the RNC. But what happens is actually that a packet that arrives here takes quite a while to arrive there. So if you would want to do an interactive traffic, that gets pretty slow, and also the elements above will suffer from the fact that the buffers are huge in between, or unexpected huge for the application layer on top. This is what I referred to when you remember to this first picture where I said, let's go, yeah, this would be how your application or your web browser expects the internet to be. But in fact, your internet, if you use a mobile, is not that trivial. Because underneath this is what basically packet for packet will arrive here. Let's say any, here. This will arrive here. And from there on, it will be repacked. It will be another IP stack. It might be ATM. It might be SDH. It might be several different transport layers. In the best case, in your home network. In the worst case, a roaming network where it's routed from Austria to here, London, or back, or something like that. And then it will only arrive to you. So basically, it is unexpected intermediate interaction. And what does this TCP do when it sees high delays, for example? It will expect that your capacity is low, because it expects that there was a congestion or something like that going on. So therefore, you will receive less data rate than you would actually be able to have capacity for. So there are certain interactions going on, and this is why I introduced these elements and their functionalities as a first step. Protocols. That is a picture I like a lot, but don't worry, I will explain it, or try my best to explain it. What that picture should show you is the protocol structure and the hierarchy of UMTS. UMTS, as we have discussed it, we have the mobile station, again, this little thing here. Then we have the node B, which can be seen here as nothing else than a high-frequency audio system, basically. We have a radio network controller, which is the thing that really does the work for this, basically. And we have the SGSN, which is basically the first counterpart that has some useful interaction on a higher layer. Why are there these three columns? Well, there is the element of signaling, which is like the first part, which takes care, for example, of radio resource controls. There is the element of circuit switch. So in case, yes, you can do voice call with these things. My children don't believe in me when I say that, but I think it's still true. And what they believe more in is packet switched information that can be transmitted. That would be the third column. And the idea to display it like that is that basically two of these always have to coexist. So you need the signaling to take place when you want to do packet switched information. Or in other words, the mobility management and the radio resource control and the radio link control have to take care about setting up some kind of connection to a base station before you're able to transmit any kind of information or IP packet. So this blue box would terminate at that side, or this column would basically always talk on these elements. So we would flow basically here, we would go up here in the frame protocols, would hand over to the RNC, where we can again go up like that, and then we have here already our GTP tunnels, which is somewhat a safe place already. What you also see is that we have two layers. One is an access stratum and one is the non-access stratum. Well, the lower part is typically what you cannot see. This is what I meant with what the mobile network does for you. The upper part would be then where we have IP, what you can access. So this would be the information that you transmit, the voice call that you do, or any further information that you receive. Just to show you that there is now not only an interaction between the boxes, but also between these signaling planes. So the signaling plane will do something, and your data plane will do it in cooperation with this. How would you notice that? Well, if you tried to connect to the internet, for example, from a mobile phone, and you would run a ping test, you will see that the first ping that you send, let's say in UMTS, will be, educated guess, 200 milliseconds. Don't kill me if it's 300 or 150, but it will be pretty large. If you then transmit something in a browser or any kind of larger file, your ping will drop to something like 60 milliseconds. Why would that happen? Well, because the signaling plane in the beginning establishes a context for you, but it doesn't provide you any credits. It says, well, the user has established a data context, but he hasn't requested resources. So what's happening then is, when you request resources, you will get a quicker, or let's say more capacity and bandwidth, so all the follow-up pings will be at a lower delay. That is, for example, crucial if you want ever to measure delay in a mobile network. And it also tells you already the problem if you want to measure delay. Because the network is actually reacting to the traffic that you offer. The more traffic you offer, the more capacity you get, the lower your delay will get, for example. If you don't offer any information to the network, or if you don't request any data, so if you go idle, your ping will be very large. You might be in a random access channel. It might be even more than 200 milliseconds, for example. And that is also true still in LTE, because it is a credit scheme for resources, where you get more credits when you request more data rate, basically. So just to give you an overview how this interaction could look like. Yeah, to show you one of these ideas, how this control plane would look like, this should just indicate we would basically have a control flavor of our GPRS transport tunnel, and this would talk through the mobility management with the radio access, so with the run-up protocol in this case. So that would be taking care of your context management. This is what your control plane would do between the GGSN and the RNC. This would be what the user plane would look like. So the GGSN would take the IP packet, it would encapsulate it in a GPRS tunneling protocol, would use any kind of transportation protocol, UDP, ATM, whatever you want, transport it to the SGSN he has selected or he thinks is the next best choice, and the SGSN itself will then pack it in a way that the RNC can understand it and transmit this information to the RNC itself. This is basically then the conversion protocols and the radio link control that the RNC would use to tell the node B to transmit these informations. So this would be an interaction between control plane, establishing your context, and then the information, the IP, that is transmitted, like we said in our example of transmitting an IP packet. So we talked a lot about mobility. One of the procedures there is GPRS mobility management, so this GMM. You will pretty often face that. I have already introduced it to you. We have, in the simplest case, 3 states. We have an idle, and ready, and a standby. Idle would be if your mobile is not attached at the moment. So if we want to leave the idle state, we have a GPRS attach. We go back from the ready state with a GPRS detach. So that would be getting ready to transmit any kind of information. If you are in the ready state, either you transmit constantly packets, then you would stay in the ready state, or if there is a certain timer that expires, you will go to a standby state. New PDU will put you in the ready state. If you don't transmit enough data for a while, you will go back to the idle state. If you want to do the experiment, give it a play, connect in the UMTS network, send any kind of ping, for example, do the download test I proposed, send again a ping, you will see a low delay. Then wait. Typically this timer is configured by the operators itself. Wait for, let's say, roughly 5 seconds, and you will see that the delay goes up again to a value of 200 milliseconds. Wait another 30 seconds, and you will be implicitly detached, for example. The delay will go up to 500, 600 milliseconds, because you're in a random access channel suddenly. So you can easily play around with these elements itself. As said already, these are configurations that the operator will do himself. Yeah? So it might be that you end up in some network that have this timer set to 1 second and this timer set to 10 seconds because he has simply too many users in the network. And every user that is connected to the cell needs some kind of resources. So he tries to get rid of the users. And there might be another operator which says, well, I have very expensive tariffs and I want to offer great kind of service, so you stay 10 seconds here and 1 minute here, for example. So this is a way to configure performance as a trade-off to the load in the network itself. So what was the next part? We talked about the radio access network application part. That handles all the signaling between the UTRAN and the packet-switched core network. Yeah, remember, there was this protocol that connects the RNC with our SGSN box itself. So what this one takes care, well, we said there is an underlying network which we need to transport our packets. So someone has to book ATM lines, change the setup, request quality of service, and tell basically the underlying network, well, I would like to transmit information. So what can it use? Well, there are these 3 elementary procedures. We have the control service, notification service, and the dedicated control service. And typical functions are to release an IU interface, for example. If you remember, we had UPS as the interface between an RNC and an SGSN. The overload control to basically take care about that packets are lost because the RNC cannot store them anymore, or a radio access bearer assignment. There was this part when you tell the RNC, okay, you found the user, please start to establish a radio access bearer, because you also have to handle these elements. So basically how that would look like, you would have the GMM on top of the run-up, and then we have our signaling connection control part, so the SCCP, which is basically the abstraction layer. That's just the abstraction between your transport system and your information that you want to transmit. So these would be the 3 layers to use for transportation. Now we have talked a lot about the GPRS tunneling protocol, and this is basically the main protocol you would work with in most of the time, because this is the protocol that transports any kind of user information or control information. The payload is basically taken and attached with a unique identifier for a user, which is basically the tunnel endpoint identifier, which is this one. And this identifier is what identifies your mobile. Like an IMSI identifies your SIM card, this endpoint identifier will always be the one that identifies the user itself. So this is a unique identifier that identifies your PDP context in this case. So, sorry, yeah?
Can you explain a little more about what an endpoint is?
Sorry, yeah. The idea of this tunneling protocol is to establish a tunnel between the entry point of the GPRS, the TGSN node, and the mobile itself. So if you feed any packet into this kind of tunnel, it will drop out at the given mobile itself. So the endpoint is then the mobile itself, and this endpoint identifier is a unique identifier for a tunnel where the packet that is put into the GGSN will arrive at the mobile at this given quality of service sources.
So it is unique to that connection?
No, it is unique to that network. If you take that identifier, it belongs to the PDP context you have created. You could create more than one PDP context, but actually the real functionality is not only to find the mobile, but the second part is, we talked about that the nodes in between have no understanding anymore of your traffic because it's packed already. We cannot look inside anymore. So you need a way to tell these elements how you transmit quality of service. And that is basically the way how you do that, because when you establish this tunnel, you basically also transmit, or you signal, this is this kind of data rate that is expected, it's this kind of delay, it's this kind of packet loss. Because you have to consider, if you go to the RNC has actually, if we look here, in this protocol stack, has no concept of IP anymore. Huh? So how would this box basically fulfill your quality of service? It has no understanding what your quality of service parameters are, and it also has no understanding how to fulfill them, basically, because it doesn't see your payload anymore. So one of the ways is basically, and that's actually also the reason that the GTP tunnel ends here, is to signal on the other end of the GTP tunnel and say, these are the expectations that this user has in this context. That's also a way that you have some operators offer services like video streaming or something like that on different, let's say, PDP contexts, because then you will have more than one tunnel, and each tunnel has then different quality of service settings. So this is a way how you transmit quality of service through the mobile network itself on, let's say, this abstract protocol level in this case. So the typical way how you find or how you find the tunnel on the other side, or how you request your profile, is this APN, because the APN will be the one that corresponds to a basic profile. You might have seen in the beginnings you had to set your APN, you had to configure that. Still nowadays, sometimes there exists an APN for free access, like at least in Austria we have this virus scan, so the virus scanning APN is for free, so you can always download new virus updates and stuff like that. So you have a free way to communicate data rate, but at a low quality of service or at a very limited IP range in that case. Yeah, we have the two flavors. We have on one hand the control tunnel that basically always needs to exist because it takes the functions of creating or updating the PDP context, updating in terms of more data rate, less data rate, or respond. And it also contains request and response for an echo message, so basically pinging, and radio access networks. So this is the part that takes care of the controlling environment, while this is a part that takes care about the user plane itself. So that hides all the mobility on the IP layer and supports the reordering of any kind of packet data units. So we have these data transmission, setup, release, error, or the echo of these elements. So, summarizing, and I will not stress you more with these protocols for the first stage. The idea here was to show you that we have this hierarchy. We have on one hand the non-access and the access stratum. So the elements you can access as a user, the elements that the mobile network itself will manage on its own. We had the core network protocols. On one hand, we have to take care about mobility. On the other hand, we have to take care about the radio access network. So we have to find a way to access our bearers. We have then the abstraction between transport layers and the information we put in. And last but not least, we have this GPRS tunneling protocol, which takes care about finally transmitting your data. You know? So every user that is active has at least this pair of GTP tunnels, so control and user plane, and will be, with this, able to exchange any kind of data in itself. Now you already understand why the SGSN is quite complex to handle, because an SGSN, which, I don't know, I think in Vienna or let's say in Austria there might be 4 or 5 of these boxes. They take care about 1 million user sessions of PDP contexts and track them in a constant manner. So this is the complexity that is put into this box. As we will see in LTE, this comes also at a price, because if you look actually at this structure, let's start with this structure. What do you think is the problem if you have a structure like that? Any guess? So on one hand we said this is the box that has to take care about all the signaling of many users. So it needs to have quite a lot of processing time. Yeah, we have to transmit the protocol, so we need also some caching. But you can also imagine if there are 1 million users on that side and the internet on that side, you will have interface problems at some time. Because actually all the data has to flow through the box. And if if we then go to LTE tomorrow, or in the afternoon, you will see that the first solution in LTE was that to reroute the data traffic on the outside, because we just said if the GTP tunnel is established, there is no need anymore to talk to the SGSN because the tunnel is there, the information has been exchanged, the data can flow to the base station. It doesn't need actually to go through this box anymore. So you see already how this has historically grown. In the beginning where in UMTS you have some 100 kbit per second per user, then this is not a problem. But if you now have, I don't know, 300 Mbit per second as a user, then this starts to get a tight link, or let's say an overloaded link in that case. Okay. So, how do we deliver that to the users? I will not stress you too much with these physical and logical channels, but I will still touch them, because this is actually very important if you want to understand how your data is then finally delivered to you. What you break it down to is, you break it down into physical channels, which is the lowest layer, then the transport channels, which would be one layer up, but still unidirectional, and then we would have logical channels. Only here we would have the radio link control, which then transmits data between you and the device itself. So the physical layer or channels would be the ones that provide the bearers for exchanging, let's say, bits in the way, but would be unidirectional in this case. The transport channels would be then the one that already are on the, let's say, OSI layer of the Mac, that are capable of, for example, a pilot channel or informations like that. And the logical channels would be then the one that are bidirectional. So basically that would be the reasons why this pointers go in two directions. And this would be what you conceive as a traffic channel in this case. Why I split it up in this way and why I want to introduce it shortly is a lot of phenomena that you might measure in the upcoming months, years, whatever, might be explainable because this one is mapped to very unique situations on physical or transport channels. Yeah? Let's start with a very simple question and a very simple technology. Simple technology would be GSM, and the simple question would be, how would you map a low data rate to a logical channel if you only have 8 time slots? Every time slot is the same, and in each time slot you can transmit a certain amount of bits. So how would you come up with a solution where you say, I only want to transmit a broadcast message. I would just want to transmit my cell ID. I don't need actually a time slot. I would need actually way less. Well, the first solution that GSM basically came up, they said, well, we could make something like frame structures. And frame structures basically was to steal time slots on a regular base. Regular in our case, just give some numbers as an example, would be every 6 seconds you create a frame. So every time slot, every 6 seconds corresponds to something that they call a super frame. Or every 120 milliseconds we have a multi-frame, or then we go down to the time slot itself. This basically explains to you if you, for example, turn on your phone in GSM, it takes quite a while until the phone is able to register. Because this information is in a super or then even in a hyperframe, which is 3 hours, for example. That would be if your encryption fails or if your roaming fails in the beginning, you would need quite a lot of time until you catch a complete frame of this. What does that actually mean if you look at any signaling message that runs over such a frame? Well, obviously, this signaling message can only appear every 6 seconds. So you don't have a continuous data flow anymore that you would expect here. Because here you have, well, basically constant data flow. But here you would only have a data flow every discrete timestamp, so every 6 seconds, for example. So handovers or elements like these, handover control, or let's say if you have a cell that is overloaded with handovers, would typically behave in a 6-second or in 120 millisecond behavior, rather than in a short behavior in this way. How is this done in UMTS? Well, in UMTS we had these two structures. If you remember, we had the control plane in parallel to the user plane, and then we have the radio resource control on the left side, which takes part of the control plane, And on the user plane, we have basically the convergence protocol or a broadcast protocol to transmit information with the RSC. Again, we have these 3 layers. And if we look at the 3 layers, well, okay, first the protocols. The convergence protocol does the same as we discussed before. It removes basically, this is what header compression, any headers that are unnecessary. Why can we remove headers? If you swap back, we said if the GTP tunnel is established, it's very clear that you go to this mobile. So actually all the information that you have about, let's say, IP headers or TCP headers or something like that could be redundant on the way from A to B, because you will arrive at a certain endpoint. This can be exchanged once and doesn't need to be exchanged anymore. You would need an abstraction layer, for example, version 4 or 6 of IP, and other, let's say, optional implementations that I put not used because there are quite a lot actually in the beginning of the standardization, but I have never seen them really activated. Most of them are also based on the fact that you always have a one-to-one identification between the core network and the mobile itself. The radio link control protocol can now run in 2 modes. One is a transport mode, where we have basically a direct passing of packets, and the other one would be a non-transparent mode, where it would support retransmissions and stuff like that. Why would we offer these 2 kind of modes? And this is actually also the reason I still put them there. Well, if you want to have data securely and efficiently transmitted, you would do a retransmission. However, if you're time-bound and you do, let's say, a real-time interaction between 2 elements, the data that you retransmit might not be of use anymore, or the application above would like to take care. Anyway, the main functions that we will have would be ciphering, obviously, flow control or segmentation, and error correction in that. Multicast would be typically cell broadcast informations and any, well, it takes care of storage and planning, but would be any kind of pilot information that you exchange between A and B. And the radio resource, so the control element, we have to some extent already discussed before, takes care about establishing the connection, so basically the bearers, routing your mobility, so basically finding the mobile if it has moved, broadcasting the control information to you or back, and then having the elements in a transfer mode itself. If we go back to the RNC, maybe like this, let's go here, you see that this would be the protocol that it uses for the node B to inform basically, or to set up these informations between these 2 elements. So to transmit this information. So, yeah, how would logical channels look like? Well, I think this is not an extensive and complete list, so just to make you aware that there are quite a lot of these. We would typically have a broadcast control channel, which contains any kind of information that your user equipment would need to attach to the cell. Timing information, power levels, network identity, cell identity, all this information. We have common control channels, which would be for exchanging your user equipment information. So if you want to register, you have to find some kind of control channel. Typically, these are also not synchronized, because this is one of the issues. How do you attach to a network when you're not synchronized? Then you would be able to use dedicated control channels, which you could use to exchange these informations. And you would also be able to be hailed by the network or alarmed, which would be paging. And counterpart would be common transport channels, where you're not synchronized, or dedicated when you're synchronized and have a dedicated channel itself. So the transport channels itself, I have already to some extent discussed that, would be defining how information can be transported and specify a certain quality, like power level or access or also delay. If we go back here, we see also that if we are in a common channel, we are typically not synchronized, so the delay would be larger. Again, we would fall back to this procedure. A common channel is typically connected to something like a standby or an idle case. So something where you are not actively transmitting data. So let's jump here. So how would they look like? Well, they are pretty similar named because they are one-to-one mapping most of the cases. We have a broadcast channel where we have downlink direction, obviously. We have a fixed bit rate. We are transmitting always the same information. We would typically use a high power level, and we transmit our cell information. We have the random access channel, as discussed. We have uplink random access, for example, where we are trying to access our network itself. We have a dedicated channel, which we can use to exchange information between the user and the base station itself. And we have a downlink shared channel, which can be used in downlink direction and shared between several users itself. Well, yeah, there's no uplink shared channel because we cannot indicate the sharing in the uplink that easily. This is why we have a random access channel. We have basically a common pilot channel, which is used to transmit our spreading sequence, for example, common control channels, dedicated physical channels, primary synchronization channel, and many more. These are basically just named to show you the complexity you end up at some point, because you see that actually all these logical channels can be in different ways mapped to transport channels, which then can be mapped in different ways to physical channels. That is one of the ways I will show you later, or one of the reasons that in LTE this has gotten much simpler, so to speak. In fact, actually this is a pretty complete list of all the channels that you could have, but not all of them were implemented in all of the networks or online actually, because not all of them are needed all the time. Why did I mention these channels? Well, we had discussed already the random access channel. There will be a different behavior of your device if you're in a random access channel, in a forward access channel, or in a dedicated channel. And therefore you would have different performance values depending on your traffic in itself. A short excerption also, how is your data really transmitted in a way? Well, this would be something like your IP packet. If you want now to transmit that, well, in the first step, you would have to boil it down in radio link packets. So you would shorten the blocks, add radio link control informations, like number of packets. Then, in the logical channels, you would typically get the MAC. So you get additionally a header. And then you would have to fit them, for example, in transport blocks, which in UMTS, I think, are 320 bits, for example. So just give you a number, 40 bytes in size. So that also explains to you why the errors that you would receive on the physical link might map very differently on the higher layers itself. So if you lose a transport block, this will typically have different impacts on the higher layers. It might also have impacts on the higher layers. In fact, if you measure arrival time of packets, it also happens from time to time that one packet will arrive before another packet. Also, it was differently injected into the core network itself. So it might be that on the way you have a reordering of packets due to the delivery of the transport blocks or the retransmission of the transport blocks. How would it work with the control channels itself? This is just an example to show you how you would establish a connection with a transport channel and a control channel itself. Well, you would basically run through the steps we have discussed before, and then you would start to interleave the data that you have in the dedicated transport channel with your control channel in parallel. So that would be the place where you then transmit block by block, containing both informations at once. And this also shows you this intermeshing between these two elements in the case. Okay, so we have basically done a very basic introductions into UMTS. Now, how would we come to anything a bit faster? So, high-speed packet access, basically. Well, in UMTS, in the very beginning, we had kind of circuit switch resource assignment. So every user got a packet switch connection, but it had a certain kind of data rate. So you had a very dedicated resource, up to 384 kbit per second. And it was not very flexible in the end. So the first step was that basically, in the high-speed packet access, what we introduced was a more flexible way to access the data itself. So you could access actually data in a kind of packet switched format again. So each TTI, which is the shortest transport time interval, was reduced from 80 to 2 milliseconds. And within these 2 milliseconds, you can have different capacity. So every 2 milliseconds, you can have a different resource. What was necessary for that was to introduce a shared channel, because you need to share this channel between the users, and you have to basically shift the scheduling to the node B. So if we consider the information from before, we said actually all the information stopped in the RNC. That was the first major change, that you move to the node B. So with HSPA, you're capable of processing your data in the node B itself, and you can reach higher data rates, but yeah, that's just a side command on these. But actually the core message is that the data processing can take part in the node B itself. Yeah, that is a time variance in these ways. But let's finish it like this. So how you can imagine that would be that you have 3 different users given in 3 different colors. And for each TTI, you would be able to transmit in different data rates or assign different resources. That is a bit, let's say, tricky in the first place, because you have to signal that. So you need to have each of these shared channels needs to have a certain control channel that allows you to signal the information and the flow between that. And that was the reason that we moved this to the node B, basically. What the node B then can do is it can do a fast retransmission. So we have a hybrid RAQ, basically, and we can schedule our information based on the user itself. So we would be actually able to guarantee either fair data rate or round-robin scheduling. So we can actually start to be a bit more flexible in the data service that we offer to the users itself. Yeah, this would be quite extensive list of new channels that have been introduced, but I think I will leave them in the slides and not stress you with that too much. What I would like to show you is actually this operation timeline. So what would happen is basically when we want to transmit data, then the UE has to report basically the link quality. So it would report the link quality. The node B would then select the UE for transmission and report the code slots it has to use. If you saw before, we have to report somehow where to find our data. Okay? So this would be the dashed line is the first TTI. Then we have the second TTI where the information where to find your data is transmitted. And then we would have the third TTI where we have our data present in that case. So this is roughly the delay that you would expect in a network like that. So it would be TTI based. It also explains to you why the TTI is the element that they try to reduce generation by generation. So we started off with 80 milliseconds in UMTS, boiled down to 10 milliseconds in HSPA, boiled down to 2 milliseconds again in HSPA, and now we are at 1 millisecond or even below. So this is why this element would be an information. What you see here is also if there is some corruption in your data, well, the fastest time that you would get your data would be another 3 TTIs. So you would gain 6 milliseconds. It's not anymore a fluid process, but it would be dedicated on the next iterations. And here we would basically signal that we have received our information and data, we have processed it, and we would report the next CQI value. So we would indicate our quality. How this works is basically, just in a short overview, the data block or the TTI is divided into 3 slots, and each of these slots can carry a different information. That was the reason why we basically painted these, also a bit shifted to the TTIs itself, so you're able to transmit information in a way like this. So you can transmit the acknowledgement and then the CQI, which gives you time to process the first element and then decode the data afterwards. Yeah, so that would be basically just what is discussed here. So we have a first part and a second part, which could be also used to identify what is your data that you want to decode and where is the data to be found, in which TTI. So we can actually go down below 1 TTI, also in HSPA in this case. Hybrid REQ was the first time introduced in HSPA. It's not a new concept at all. But as discussed before, we had this issue in the beginning that the RNC was the last device that was capable of decoding data. And the RNC was pretty far away from the mobile itself. So the loop that was happening between the RNC and the node B was simply too long to retransmit information or to apply any kind of coding like a hybrid REQ method itself. And therefore, the first time in HSPA is that the base station itself is now capable of retransmitting information that was given by a failed packet itself. However, if you would look, that's the wrong slide, maybe I'll show you that one later. Where is it? Sorry. Here. However, if you would look into something that is, let's say, 10 milliseconds TTIs, and you transmit or you ask to transmit data, you get granted, and you transmit data, so that would be the typical advice how you would transmit data now. The challenge would be if you would signal that a packet is lost, you would still at least need 3 TTIs to retransmit this information. So the duration that you would need is, even if you're in the node B, would be 3 TTI units typically that you need to transmit this information. So roughly these 14 to 16 milliseconds that you would see. And in fact, if you make measurements over a longer period of time in a mobile network, you will see that either the packets arrive at a certain time, let's say 20 milliseconds delay, or at another 14 or 16 milliseconds of iteration as the time that it needs to reprocess this information. Just to give you these as information this way. So where did we stop? Yeah, basically what I introduced here was first we had the downlink, now we have the uplink part. The uplink part is basically very similar to the downlink part. However, the big difference is that in the downlink part, the base station can schedule, which is pretty easy. So the base station can tell you where to find your data, and the base station has information where your data is, or how large your data is, because the stream is coming downwards. In the uplink, it's the contrary. The device actually has to say, I would like to transmit data, and the base station has to grant you this information. So it's basically a credit scheme. So in uplink, you ask for resources, the base station grants you resources. This is a typical thing if you, let's go back to the simple example of a ping test. If you would do a ping test with a normal ping size, you get a very low delay. You have done everything, you have done the pre-charge, you have done the preload, so you have now your dedicated channel, you know you have your resources, everything is fine. You do a ping, and you will have a low delay. You do another ping, after some time you again have a pretty low round-trip time. What's happening is actually that the base station itself in the uplink already grants you, on the first iteration, I guess 32 bytes for a ping. If you would send a ping with 40 bytes or 45, depends how greedy your operator has set the network, you would suddenly see a delay that is 30 milliseconds higher. What's happening is that when you ask for granting your resources, you get automatically a first set of resources. When you have used them up, you have to ask again for more resources, so it's an iterative process with a window that is growing in the uplink, and therefore you will have an interaction between the size of packet you send or the data rate that you get. So this is also a way to find an optimum between the delay or the configurations and the round-trip times that you will have. This is basically summarized here in this basic operation, so that you would do a transmit request, you would basically receive then the scheduling information, and you would then increase this information or the resources that you transmit iteratively every time that you upload data information. Yeah, that is just to complete the different names of the data or channels itself. I put them there to have at least heard them once in the first snap and see them in this case. Yeah, and that was the example that has shifted a bit. Maybe we can go through it again to remember that. The point was that you have to request resources. You will be then granted these resources from the base station and then be able to send data on the granted informations itself. If you would now increase your data rate, or if you would like to send more data rate than needed, you would need to renegotiate basically with the base station, because the uplink cannot be scheduled from you, but it has to be scheduled with the base station itself. So the uplink is typically much slower than the downlink. It's the same principle that you would also see in LTE, because also there the uplink is to this extent shared, so you cannot just take all the resources that you would that you would have or like to. Okay, so short wrap up to close this one. We have reintroduced, so to speak, packet-oriented data transmission. Why reintroduced? Well, as we have discussed before, UMTS was basically assigning fixed data rates to every user, so you had a fixed capacity on your link. It was some kind of circuit switched in packet switch, so you got a certain capacity and transmit your data. In HSPA, we have packet transmit data again. We have obviously a lower delay because we have shrunk our TTI, and we are much more efficient because the node B is scheduling our data. We're efficient in what? Well, in retransmitting, so we are basically able to recover from errors. But we are also more efficient in transmitting in case of a handover, for example. Because the node B has now a concept of your packets, and therefore you're capable of forwarding these packets if you move to another cell. Because in fact, we have had a short introduction to some protocols, but what happens if I change to another cell? You have to imagine there are some packets that are in this base station, and you have moved to the next base station. So you have to basically cancel those packets. You have to find them again or retransmit them. In the worst case, you have to tell the internet server, this TCP packet is lost, please send it again. In the best case, and this is why that improves performance quite a lot, the base station forwards this information to the next base station. Actually, the handover process goes hand in hand with these informations. Yeah, basically what we talk about when we talk about different evolution steps in UMTS, we talk about releases. Maybe to catch up, the first release is typically referred to release 99. HSDPA, we have release 5. HSUPA, we have release 6. So that would be the evolution that we're going on. Nowadays, we would talk about roughly release 12. 5G starts somewhere at release 14, 15, something like that. So it is more a, let's say, very fluid move from one technology to the next. While GSM was really a cut, now LTE Advanced, that comes from UMTS, is release 8 and ongoing, and 5G will be something at release 14, 15, something like that. So this is a continuous flow of these elements. Now let's do this last journey. We have a payload, and we would like to transmit the payload from, let's say, a user to any kind of internet device. So this is our phone, our payload. We would like to send it there. we have learned we create a PDP context. This is our unique identifier between A and B. This PDP context creates us a tunnel between A and B. So we have now a unique identifier that the mobile network knows. If you remember, this tunnel was always given the quality of service, like the delay, the data rate that you're acceptable to check. It also contains like charging, for example, so the GGSN will keep track of your spendings. If you have a prepaid tariff, for example, the GGSN would cut the tunnel in the worst case. However, it is also known to all the other devices. So now all these stacks here will take care to transmit your payload. What would be the step that creates the PDP context, just to show you how these, let's say, procedures that we have shortly seen would work? Well, we had the mobility procedure, which you can use to ask for attachment. So the mobile phone will connect with the mobility over a random access channel to the SGSN and say, please attach me. The SGSN will verify you on the home location register, so it will basically check your IDs and your key that you have provided, if it's valid. If that is the case, it will approve your request, and you can start the activation procedure, which is nothing else than establishing the radio bearers, establishing the GTP tunnel, and making all the information ready to transmit user data. And now we have arrived in this state to transmit our user data itself. How would that now look like? Well, we can start with any kind of image, having a certain size, which would be broken down to TCP packets, for example. I guess that's nothing new in this case. Then we would attach GTP information, UDP, and IP information. At some point, we might break it down to ATM layers in small packets and transmitting these informations. So basically, in your mobile network, your payload would look like basically the payload, your IP header, a GTP header, a UDP header, an IP header, then maybe ATM, SDH, whatever. So there might be another subset of layers or headers on top of these elements. Why is this also interesting? If you're ever facing the quest to track delay between here and here, you have to be aware that here your packet might consider or consist of many other packets. Actually, for sure, it will consist of many other packets, especially here when you have ATM lines, for example. So there is not a one-to-one matching anymore possible between the different interfaces. It's a quite uncommon problem in the internet, because typically if you go into a box and if you go out, it's still an IP packet and nothing has happened. But here it's actually, you go in and you go out, and the packet might look completely different, because it might be broken down into smaller packets, or it might be reassembled with other packets, for example, and elements like that. So inter-packet delay doesn't make that much sense anymore if you measure that. It might be that two packets are suddenly back-to-back. They have just been put into the same TTI or into the same transport protocol stack here. Might also be that they have been reordered because the fitting or the retransmission happened simply somewhere on the physical layers. So you have to be very careful what you consider delay between different interfaces in the mobile network itself. The packets basically would now travel through the network. The GTP tunnel would give us all the information we need to route between SGSNs. The UDP and the IP would basically contain the IP addresses of the next box to go to, so either an SGSN or a GGSN or another SGSN roaming, whatever it would be. And finally, at the GGSN, what would happen, he would take the information of the GTP header, and basically you would get an IP address translation. Typically, you will have a private address inside, you will have a public address on the outside. So what he does is he takes the identifier and he changes the IP address to your outside. Might do some firewalling, deep packet inspection, NSA, whatever copying that would happen in this box, basically. Yeah? So typically, for example, if you have a billing that is based on the content of your data, that's also what's happening in the GGSN, because this is basically the first box or the border gateway that takes care about these elements. Yeah, and then we basically arrive at some Stone Age phone or laptop in our case. And yeah, so last question to brush you up. Where's the bird in the picture? Found? I hope so. Okay. That was maybe a bit intensive, but kind of crash course. This is why I will provide you the slides. But I hope I gave you all the, let's say, the most important basics of GSM, UMTS, and procedures. The next round will be then purely focusing on LTE and focusing also more in the direction of IoT and advances in this direction, and the expectations you should have in these. Things you should definitely take home with would be the IMSI, so the identifier of the phone, the GTP as an identifier of your data flow from A to B. Elements like RNC, SGSN, GGSN, Node B are interesting, but basically the functionality is interesting. You need a mobility anchor, you need a data anchor. So the SGSN would be the mobility anchor. It knows where you are, where you go. The GGSN would be the IP anchor, so the data flow goes through the GGSN to somewhere. And RNC and Node B would take care about your radio link. Could be anything else in modern networks itself. Yeah, the main interface is most likely you will, if ever, face GI and GN, which are the interfaces to the internet or to the SGSN. These are the most easy to understand. What you might need are PDP context and mobility management as procedures, because this might be the procedures you will face the most likely. Whatever you do with devices that are not permanently connected, that are connected on and off, for example, or smart metering or elements like that, will have to do a lot with mobility management, for example, and creating PDP contexts will be mainly interesting for establishing different quality of service. So if you want to transmit different quality of service to different users, that would be the elements to know. So, thank you. I nearly made it on time. So, questions? Stressed. I heard there's a coffee break, so you can also ask me in person if you want. If that is a better solution.
If there is no question, I think we can have the break now. And we start in 30 minutes. Thank you.
Thanks. Okay, so welcome back. Thanks for joining again. The second part will mainly focus on LTE and follow-up developments like IoT, for example, and also discuss some measurement results and give some hints for solutions. I already announced it now. I will invite everyone who wants for writing me an email for a homework, because I actually prepared a short homework example where you can try your skills on all the things you could see in a network, outages and describing of test procedures and everything that could happen to you as an engineer's life or being the customer to engineers. Okay, let's start off with LTE. Basically, let's say generation, it started in 2004. We had these long-term evolution, and it was introduced first with release 8. As we have described before, we have these releases. If you remember, 5, 6 was roughly the time when we have introduced HSDPA, HSUPA, and release 8 was the first release for LTE that was going live. Historically, roughly 2010 was the first deployment of LTE, and since then we have more and more growing in LTE. Motivation is the growth in data rate. And as we have touched before, the core network was originally not really targeting anymore these data rates. The data rates for the customers have also grown quite extensively with LTE. We typically have data rates, 600 Mbit is now the newest release, but 150 is maybe what you would see most commonly, or 100 Mbit in different categories. Upload is between 100 or 50 Mbit, which is always limited due to the fact that you have limited amount of antennas, but also limited amount of power in the device. This is also a big difference in LTE. In UMTS, you still have results or implementation configurations that are used for phones, In LTE, you have now massive MIMO approaches like 8x8 antennas. And if you look at a device like this, then, 8 antennas, given that knowledge about lambda of wavelengths, is not really possible if you don't go for millimeter waves. So they are dedicated for devices like this. So a notebook or anything where you can really place 8 different antennas, or 4 in different polarizations, for example. We target lower delays, and we target, obviously, the cleaning up of the core network. Because we had a core network for voice, we have a core network for packet switch, like double the elements, and we had these elements where all the data rate has to flow through, so that was not really optimized in any way. Yeah, this is actually just a repetition of before to show you the different releases. I guess I can jump over that to catch on some more time. Release 8. The first release was basically targeting 10 milliseconds of round-trip time. We had 150 Mbit of data rate. We have a major change that is maybe not so prominent broadcasted, but we are flexible in bandwidth. That's not the fact for UMTS that easily. So you can squeeze in LTE wherever you want. This is the reason you can refarm, for example, GSM at a certain price, because the overhead in LTE is pretty high, and the smaller you make the bandwidth, the more overhead you have. You can also do carrier aggregation, which means you can have multiple of 20 megahertz in case of the newest releases, also in different bands, so you can actually reach pretty high data rates. There's a change in the physical part in terms of OFDM and the single carrier FDMA. So we have a different way to access our grid of information. We have shortly touched in GSM, it was time-based, so we had a TDMA. In UMTS, we had a code, so a CDMA. So different codes allowed us to use different resources. Now we have a combination of frequency and time. So we can spread our information either in frequency or in time itself. So this is where the newest grid would come in. Yeah, and we have basically something that is the system architecture evolution, so the SIE or the evolved packet core, so the new all-IP packet core of LTE. The next release basically focused on femtocells. This might be something you're already working on that, or self-optimized networks. So there was the next feature where you say, I want to have small self-organizing entities to deploy, for example, indoor scenarios, and I want to optimize these indoor scenarios. I had then MBMS, so that is basically a broadcast system where you're broadcasting video streams. That is something that works in some countries, but not everywhere. You have to understand the broadcasting system always has the drawback. When you broadcast, you have to reach a certain power level to serve all the customers. So if you want to serve people on the cell edge, you will waste a lot of power or a lot of, let's say, resources in order to be able to feed these customers. On the other hand, you are able to transmit information very efficiently. Typical customers that would ask for such features are car companies, for example, for highway, but also basic operators that want to transmit information like video streaming of some events, for example. All these features are actually already implemented in the LTE simulator that I mentioned before, which is open source in MATLAB. So if you want to play around a bit, you feel free to download and just play around with either system or link level simulator. And typical example, this is why it came to my mind, is when does it pay off to use MBMS and when does it pay off to use a direct link between users to see when is it more efficient to use one of the both. Next step was then release 10, where we introduced carrier aggregation to boost basically data rates, and we start to introduce higher layers of MIMO. As mentioned before, we have 8x8 or 4x4. When you look at a base station antenna, you understand that even 8x8 is difficult. I mean, using 2 polarizations, it's just 4 antennas, but it will still be pretty wide. What is here the interesting part, which was one of the newest features we implemented, is relay nodes. So actually optimizing, for example, to have relay nodes in LTE. How long is the delay? How efficient can you link between these cells? And interference coordination. So this was done optimizing the cell edge in this case. Yeah, we had then release 11, which mainly was a refinement release, where we have more carrier aggregation, relay nodes, new frequency bands, and elements like these. What is maybe more interesting is release 12, because here we have the nice things like device-to-device communications. That is to some extent also used in car-to-car communications. We have a lot of research going on if we should go for Wi-Fi or LTE to talk between cars. So what is the more efficient way to exchange informations? TDD and FDD are optimized in this way. Especially TDD is somehow coming back. Why is it like having kind of a renaissance in, let's say, in the current context? We're going more into the millimeter waves. And if you go to millimeter waves and if you go to massive MIMO, what you need is a lot of pilot information, because you have to estimate your channel, which means you have to waste a lot of your resources just to estimate your channel itself. You can avoid that easily if you switch from FDD to TDD, because then you are basically reusing the same channel in up and in downlink. So this is basically also why one of the latest additions of the simulator in that direction was to be capable to run also TDD elements like these. Yeah, and then we have obviously the integration of Wi-Fi into our, let's say, into LTE or LTE into Wi-Fi, which is LTE unlicensed, or elements like these. So reusage of open bands. So let's start with the architecture. Well, in the architecture, as we have mentioned, as a first step is we have a new radio access, one major change. We have eliminated a lot in the radio access, so we have just one node, which is called evolved node B. Don't ask me what node B means. I also don't know why it's now E node B. Must have been a very interesting meeting when they settled about a naming like that. So obviously we have less interfaces at the RAN. You have to see that an RNC that was connected to all the base stations itself was typically connected with a lot of fiber optic connections, ATM, STH lines. Now we have reduced it to an all IP network where just the node B is connected to a device itself. We have removed actually a lot of the core network. We have removed completely the voice part. We are left over with the packet switch part, and there we have done certain optimizations where we basically split the mobility anchor from the data anchor. So they're not in one box anymore. If you remember before, there was this one SGSN, which was one box serving both purposes, and now this looks like this. So basically, yeah, if you complain about the naming before, now everything is S and the number. Beside this one, this is X and the number. But yeah, don't worry, I also myself have to look it up from time to time. The most interesting interfaces still could be the S1U, which is the one that carries all the data information, and the S1MME, which is the one that contains all the mobility information. The node Bs itself are now intermeshed. Remember this discussion before in GSM, the packet has to go back until it finds a core network node that is able to say, oh, the packet got lost, I have to retransmit and stuff like that. So it took forever. Also handover took forever. Then we had UMTS, where it was a bit faster, but still the RNC has to find the next block, has to have a TTI and things like that. Now the node Bs are actually directly connected. Well, if I draw a line here, remember it was an all IP network, that is basically a logical connection that happens between them. So obviously these node Bs are connected to an IP network, and somewhere this information can be routed to the next node B. So depending how well you connect them or how you mesh them will take some time to arrive to the next node B, but you are capable actually to forward user data over an X2 interface, and you're also able to optimize between. Here comes in the self-organizing network, so they are capable to exchange informations in that way. What is now the difference is basically we have these two new elements. We have the MME, it's a mobility management entity, and we have here on the upper part a serving gateway that is just responsible for your user data. So what happens if a user registers to the network, he attaches to the node B, and the node B will query the MME and say, well, dear MME, this is the user, this is his password, this is his key, would you be so kind and let it in? Then he will query the HSS, so the home subscriber server or the home location register. And based on this, the MME will grant to the node B the connection of the user. It will also control that there is a bearer established. What we have called before the PDP context, we call now a bearer. Pretty much the same. You have quality settings, you have information where to flow the data, but this is independent. So the MME basically hands over to this serving gateway and tells him, please serve this data flow. That has two advantages. All the processing happens here, all the ciphering and all the authentication, all the tracking, all the finding the user or keeping track of happens there. But all the data flow basically flows through a box that is pretty simple, basically like a border gateway or something like that. So could be some kind of Cisco firewall or whatever. Doesn't need any high functionality to process. The only thing that this would basically still have is a pricing gateway where he would get the policies and charge for the money that has flown through. So it has basically to indicate how many credits you have used or how much volume you have used, and based on that also set certain policies of your data flow in this case. Again, this is still there because the user data exists, like in all the other networks, up to this interface, which is now called SGI, and up to then is packed into GTP tunnels. Nothing has changed in that context. So this basically is GTP tunnels from A to B. What has changed is we just have two nodes left, and the node that processes all the data flow, so that needs to be actually high throughput, has nothing to do with the node that has to take care about all the user state informations and the mobilities. Still, we have the radio access network as before, and we have the core network element part here as before in that. What would you do if you have UMTS, GPRS, any kind of other network? Well, what's happening is you have to attach your SGSN basically to two entities, and these two entities will then allow you to route all the traffic from here into this network. This is typically a tricky connection, especially considering that this side of the network might have a voice call. So if you would want to make a voice call handover, you also see that the mobile switching center needs to be connected to these elements. So there's actually a lot of complexity added to be backwards compatible. The LTE is completely backwards compatible, but these interfaces are actually quite complex from the protocols itself, which you might notice if you ever come into the fact that you have to measure speech quality, for example, and you would do that cross different technologies and not GSM UMTS, but really UMTS LTE. You will see that there are degradations into the voice quality and changes due to the recoding and the change of codec, basically. So this is one of the remarks where you will find these elements. So, main logic nodes that we have is the serving gateway. We have mobility management entity as set for the bearers, and the PDN gateway as before. I call it IP anchor, but basically, as you know, it's the data anchor. So all the packets that go in will go to the user. This is mobility anchor, so it will always know where the user is. And when you query or when you try to alarm it, it will ping for these informations. The other nodes are pretty the same. It's the home location register, that's the same. What is different is the policy control and charging rules function, where you can set quality settings. I will come a bit later to that, why this is different, but just keep it in mind in that case. Yeah, and the radio network obviously has deteriorated or has shrunk to one single node, which has two impacts. One I named, that they can be intermeshed easier, and they have these high-speed connections. But it also means actually that all the information, if you remember before we had in UMTS the problem, the information is the RNC. Then we moved it with HSPA into a bit at least to the node B. But now the node B has actually the full control. This is why nowadays you talk a lot about optimizing energy, reducing delay and all these elements, because that can happen now in this node. The E node B has complete control about the user traffic, about scheduling, optimizing energy, anything in that direction. So whatever you want to do, you can do directly there. How would it look like now on the protocol layer? Well, we have very similar protocols like before, and we have similar concepts as before. This is basically also to give you the feedback why we have introduced like the radio resource control or the PDCP or the RLC. We have the same mobility management. There are other mobility states, obviously, but basically we use the same protocols as before, and we have extended them to some parts. As you can see, this is what I touched before. The node B is now responsible for the radio bearer control, so it can manage and access the resources, which comes in very handy. If you have OFDM, you can now access the frequency and the timing spacing, depending on the user. You have control over radio resources in terms of intercell, so also between cells can be changed. This is kind of then organizing in this way. And as we can see here, the gateway for the data is just the data mobility anchor, but the MME contains all the information about the idle state, the bearer control for modifying quality of service, and the security for the access strata. So we have the non-access strata security that is hidden in the MME now. And this is basically the GGSN from before. Because what's happening there is we change the IP address, we do some kind of packet filtering, and we have now the UE IP address allocation up and down. So the MME basically controls what? It controls the idle mode and the tracking of the user equipment in the idle mode, bearer activation and deactivation, then selecting the gateway for the user equipment. As said before, it is the one that is queried by the user equipment, and then it has to select some gateway, set up the bearer, and connect this information. User authentication, obviously, termination point for the non-access stratums, and the ciphering is taken care of. Obviously, also the paging, because it's the node that knows where the devices are, so it does the paging in these. The serving gateway now will take care about the user plane mobility in terms of it's told by the MME where to connect to, and then it will establish and keep this connection on the data LAN. It will connect the radio access network with the core network, so this is basically the last feature that is left for it. It will do any kind of forwarding and caching of user data, because the node B, again, might be overloaded in terms of user data. And it will be replicating any kind of user data for the monitoring. So that's maybe a bit different from before. Before we said we replicate here. Now, if you would try to get a trace from an operator, you would ask for the S-gateway traces, for example, because there you get all the user-related data as a copy. And yeah, basically, if the user equipment is idle, it will terminate in this gateway. Obviously, there is no need for any connections to go further. The packet data network gateway would be then the anchor for any external IP addresses. We have quality of service enforcements, then the filtering, so any kind of data that is filtered will be applied there, and we have the traffic flow templates, basically. Traffic flow templates are filtering templates on top of our PDP contexts, which then also allow us to do charging or application of the qualities. Charging basically also on the URL, because in this box we know all this information already. Now we have talked a lot about bearers and not so much anymore about PDP context. Well, bearers are actually, and this is just copy-pasted, IP packet flow with a defined quality of service setting established between a gateway and the user equipment. This is how 3GPP sees a bearer. So nothing else than a PDP context from before is now defined as a bearer. Why is it called a bit differently? Well, in UMTS you had a PDP context, and the standard configuration is you had one of them. You could have up to 4 or 8, depending on the configuration, but it was actually not very flexible. A bearer is now considered to be very flexible. So actually every IP flow can be assigned a different bearer or quality of service. So there's much more flexibility now. Where does this also come from? Well, we have seen there's no voice anymore available. So you need to be able to assign a voice call another quality of service than any kind of download, for example. So you need to have much more flexibility on the IP flows. So you don't have the naming PDP context anymore. Still you have the GTP tunnel protocol in a different flavor. So it's called version 2 in that case. But it's only the control part that is called differently. Because, I mean, as we have seen, the data part is nothing else than adding this tunnel endpoint identifier. There's no need to change that. The C part needs to have a change to apply to these bearer concepts in the end. So if you set up this, you would have version 1 on the user plane, version 2 on the control plane in this case. What's interesting here is basically that these bearers are also the reason that you have now these control entity that does all the policy. So the policy gateway is attached to this. Oh, sorry.
About the bearers,
Mm-hmm.
there must be many, requests by multiple users with different bearers, with different quality of service that they would be requesting. So how are they identified?
No, the user actually cannot request the quality. Here, the policy and charging gate rules function will apply the bearer or the configuration of the bearer itself. So it's not the user that will require. I mean, if you go to the shop and you buy your tariff, you somehow decide for one policy, which is the data rate or the volume that you can transfer. But after that, the bearer will be assigned based on that.
Even the users may not be choosing it, but they would be having some different requests, which are, which would be assigned different bearers. So in a particular stream,
Yes.
how are they? I mean, are they managed with a certain protocol, identified with a certain thing? Are they parallel streams, like?
I have to admit, I never thought about that. I'm trying to think. We analyzed the impact of different quality of service settings, but I cannot answer that now. But if you write me an email, I will try to catch up on that. Sorry? Yeah, but that is something here. And actually in UMTS. So the channel quality index is something that you report back in HSPA to say how good your SNR is. But this is the policy here would indicate the quality of service that you get on top of a bearer, basically, like data rate or packet loss or minimum delay time that you are able to wait.
What is the QCI?
Or-
QS classifier.
Ah.
QCI, QS classifier indicator, that maps the specific service you would have, for instance, best effort in the streaming, and then the traffic.
Ah, okay. Now I was on a different train. Sorry. Yeah, that's true. You're right. QCI is quality. Yeah, this is a mapping procedure only. Yeah.
It's not actually the user that is deciding which.
No, this is what I meant with this. Basically maps at the moment that you get it, but I'm not really sure how the node itself implements that this is fulfilled. So this is what I was not sure about. We just analyzed what the impact was on different traffics, but I'm not really sure which method these nodes use to follow the quality between these nodes. That I don't know by heart, to be honest. So, if anyone knows? Not? Okay, then I will look up.
I think it's simply an IP. It's like who is the destination?
Mm-hmm.
There's simply an IP, different IPs.
Yeah, but I would not be sure how to.
His question,
Yeah.
because it wasn't related to radio frequency.
Yeah. It's a mapping, basically. We just discussed, but
I think that's what you meant.
okay. But
It's about how they are being processed. So, I mean, it's an IP flow. So, how is it? There's a particular string of bits that's being sent, packets. So, how are they managed in that sense? Are they, some packets? Are they transmitted in a ratio, or are they parallel streams? That way.
You mean only they go into the channel?
Yeah, I'm talking more on the
I think
physical layer.
I think it means this mapping assured forwarding and then the different levels of QoS.
how they.
The buffer is
Yes.
to this channel.
Yeah.
There is an algorithm.
But
in fact, I think 3 algorithms.
there are 3, I think, but I don't know which is.
So the operator and the possibility to choose
Yeah.
which algorithm goes here.
But
It also relates to their IP.
Yeah, but I don't know which is typically used. That is.
It goes like this, but there's the algorithms are predefined, and there's a
Yeah,
set
they.
of 3 or 4 that they choose between those.
I just know one, but I was not aware which is really used for this.
I can't remember the names.
No. I don't. I'm not sure on that. This is why I said I have to look it up. I just know the mapping here, but I don't know what typically is used to ensure it, basically, as a policy. That I don't know, I have to admit. Mm-hmm. Where did we end? This we did, this we did, this we did. Yeah, that's just a picture for that. Yeah, okay, policy control and charging function. Well, there was the box where we said we do a mapping, basically, so we have to have the data flow. We have on one hand to basically label it, and we have then to identify, yeah, there's the QS class identifiers. I went wrong. And identify the quality of service you are, this is what I meant, eligible for. So not the user can ask for it, but you get mapped, but that depends on this set of rules that you have implemented in that. So basically, this is why I listed them here, but they are the same protocols as we had them before. So we have the PDCP. So we have the typical convergence protocol here again. We have the same functionalities as before. We have header compression functions. We have in, out of order deliveries and elements like these. We have the radio link control where we have acknowledgement, unacknowledgement mode. We have segmentations, retransmission handling, in-sequence delivery, or re-establishments. So basically really a one-to-one mapping as before. What is different is the termination point, because this is now directly in the evolved node B. And what is also different in that way is, or what you can see as an impact, this is why I gave here as an example for a measurement. I tried to keep that a bit more interesting by introducing some measurements we did. This would be a size transmitted, so it would be packets with different size, and that would be the one-way delay measured. So this would be the time it took to go through the network from the gateway, so from our internet interface to the mobile itself. So when you see a line here, it's visible. So a straight line here is basically a data rate. So basically, if you have here a certain slope that corresponds to a data rate, the intensity is given by coloring, and you can see that a retransmission then would happen basically several TTIs later. This is typically a configuration parameter, and here you see that you have a lot of noise if you do a short measurement like this is, because you see it's like, it's logarithmic, okay, but it's 10 events when it's read. So basically there was just a small experiment where we sent increasing size of datagrams and measured a one-way delay, and you see that you then get basically discrete steps between the first and the second retransmission in these elements, just to show you this impact of radio link adaptations. Yeah, the access for the MME, basically, what you exchange with that, as discussed before, we do the bearer management there, we do authentication, or we do the paging. So we look for the device itself. And for all the other devices, or for all the other elements, we can make them happen in the eNode B itself. So only this will flow to the MME, and only the data will then flow to the next gateway itself. Okay? So that basically leaves us with the possibility to perform certain things. We can, on one hand, analyze the payload. We can, on one hand, set priorities. We can also analyze retransmission control. We can adapt modulation or coding. And we can finally also assign different resources or antennas in this box. And this is what also is one of these optimization things you will often play around, most likely in the eNodeB. So you can basically adapt the scheduler to different settings. This is a typical parameter you can, for example, use in the LTE simulator, or that is applied in the LTE simulator, how you would assign different data flows to different users. How do you optimize cell capacity, or how do you optimize user data rate, or how do you optimize the small cells deployments, for example, in this case. How would the bearer setup look like in our case? Very similar in this case. We have initial access. We have the radio resource control for the connection establishment. We have an attach request, authentication, security, basically exchange of capabilities. And then we basically have reconfigurations and attach with the certain quality of parameters, quality of service parameters that we have exchanged in our case. So yeah, this is basically just to show you the same as before, but we have already went through that like an hour ago, so I jumped that. Because this is actually the more interesting part. This now is much more clean. If you remember right before, we had a lot of downlink logical channels, and we had a lot of transport channels, and the mapping here was quite, let's say, broad. And in our case, we just have something for paging, which is the one to the left. We have a broadcast channel, and we have a downlink shared parameter or channel where all the others are served in that way. And if you go in the other direction, you see that we actually even go down to 2. We have a random access, and we have an uplink shared, and that basically covers all the elements that we have from this. And yeah, I have this picture. That is, I think, would be a complete interconnection like it was in UMTS before. So that is basically, from this, we went to something that is much easier and much more plain in this element, which is also possible because we have just the packet core and therefore much less things to be mapped between A and B. The voice part itself is actually depends on the deployment that your operator has. We currently do a lot of experiments with voice over IP, so VoLTE. There are certain hybrid solutions, or some people still nowadays use a circuit switch fallback, which basically means you are downgraded to UMTS whenever you do a voice call or you receive a voice call. But typically, you will do a VoLTE implementation, and this is actually what most networks will use in the future. Yeah, this is just summarizing the main changes that we had in LTE, which was we have changed our physical access, so the radio access. We have changed the procedures in terms of PDP context to bearers, and we have done major core network cleanup where we have now less nodes with different functionalities. Let's put it like that. What is the more interesting part maybe? Where do we go next? So what is 14, 15, 16, or whatever release? Well, we have on one hand the relay nodes. We have already discussed that. We have dynamic reservation of resources or load balancing. We have the discontinuous transmission. I will shortly show something to that. And we target obviously always more data rate and lower round trip times. What might be most interesting for most is the discontinuous transmissions, because that somehow points to IoT or machine to machine, and the relay nodes for evolution. So I started off with the first releases where we go from 12 to 13 to 14. We see we have this device to device we shortly touched before. We have the Wi-Fi offloading, which is on one hand that you offload your data flow to Wi-Fi, or that you go later in the next extension to LTE unlicensed. So I don't know how familiar you are with that. This is basically using LTE in unlicensed bands. So ESM bands, 2.4, 2.5 gigahertz bands, and elements like this. So you would basically make use of spectrum that is non-licensed, and hopefully boost the data rate of LTE, not at the cost of Wi-Fi performance. This is, I think, we just had a chat, you said, terrible, at least if you have Wi-Fi. I mean that you have to understand a Wi-Fi chip is typically, I don't know, €5 or less. LTE chip is, I guess, €100 in IPRs. Therefore, an LTE system in a Wi-Fi environment will be difficult to compete with Wi-Fi. So we also did some research and measurements on these, and you see that the Wi-Fi is struggling to perform nicely. Let's put it like that, in this way. But the bonus is that you have wide amounts of spectra. You have hundreds of megahertz, actually, if you go to 5 gigahertz, or other spectrums that are free, and they are free nearly worldwide, because these are the Wi-Fi ASM bands. What we also target at is actually that we have virtualization, and we do something in the direction of public safety and push-to-talk. So we try to go in the direction of servicing in terms of emergencies. So emergency services are also a major player that is coming into these releases now. As you can see the timeline, this is basically where we are now. So this is the ongoing release schedule that we have at the moment. What I wanted to shortly jump to that is that the more we go into somehow future networks, the more, let's say, dynamic our user profiles will get. So we will start to somehow split our user profiles into something that is high performance or efficiency. High performance in terms of having small latency or high bit rate at the cost of availability, for example, or power efficiency, or elements like this, or even mobility, for example, or being more efficient, so we have more battery life but less data rate, for example. So we will have different spectra, and this is actually something that 5G is targeting at. So if you, I want to make also available a third presentation to download. If you sneak peek there, you will see the different modulation schemes that 5G is using. So there's a bit more of radio applications there. There we are targeting at different modulation schemes that either are more efficient or more responsive in delay, for example. So this is the next step where to go in this direction. Okay, this is a slide I have maybe moved too far backwards. That was actually the motivation before for the volume growing. So this is from the Cisco reports. You might know them. There are the Cisco mobile reports, which are issued, and they always give a trend of the growth of volume of the data rate, and they typically show here a growth of data rate over the different years. And what is interesting is that most of that is just the mobile traffic. So the volume of the mobile traffic is really continuously pushing every year. That is also interesting, as this does not really contain machine-to-machine traffic at the moment. So these are actually two different approaches. This is why you also see different optimizations in the releases for one and the other. This is just to show you the view, because just stress that this is my view, so don't trust in it at all. This is the view that GSMA has, basically. So if you go to last year's GSMA release, they split it in delay and bandwidth, and they said this will be the target applications they want to push for. So the red ones are actually the ones that they currently push, because this is disaster alerting or automotive, so that is these e-call systems. Autonomous driving is a point that I think is moving around everywhere. Let's assume it's currently there. And all the other things like cloud-based storages or wireless cloud in the office environment are in the range of hundreds of Mbits, but maybe with a higher delay that you can accept. What is interesting at the moment, at least from our perspective, mainly is the autonomous driving, because this is pretty much a driver for a profile that you see for highways or actually rural areas that are not covered that nicely. This is also the typical scenario that you use to compare eMBMS with dedicated links, for example. because you want to understand, is it better to serve a user on a broadcast message, or is it better to have dedicated links for these users? So that is just to basically tease you again with this picture where we said we had on the top, we have our high-level web browsing, email checking, FTP, or anything like that. On the lower end, we have our packets. So typically, when we measure any kind of KPIs, we will measure packet size, inter-arrival times, how many volume do I need to transfer, and elements like this. We might even be here at the flow level. We would indicate RTT of TCP and elements like these. However, what's happening nowadays a lot is that we have encrypted tunnels. Encrypted tunnels have two disadvantages. Well, three if you want to sniff the traffic. But the two disadvantages is, the first one is that you cannot reassemble the traffic anymore, because typically the GGSN or any kind of border gateway will cache your traffic. So you're not capable anymore of retransmitting or basically breaking up the connection and efficiently cache the traffic. And the second disadvantage is that these encrypted tunnels might interact strongly with your network itself. You might see that when you stream YouTube on an encrypted traffic and you do handovers, it takes typically, you will get an outage. We did some quality analysis for video streaming with handovers. In case of the encrypted tunnels, the stream was basically interrupted quite strongly. In case when you do that with a non-encrypted tunnel, you can recover much easier, as it is basically stored here and captured in this case. This is just information for you to be considered if you do practical experiments in that way. Speaking of practical experiments, what could be interesting in that way, and that is just a teaser from my side, so if you're ever interested to visit Vienna, feel free to come by. What we currently do is a lot of crowdsourcing, so we are actually focusing on how many measurements would you need to come up with a coverage map of Vienna. Given that you have no control about the measurement, that the measurement points are randomly distributed in Vienna, and that you would try to come up with these informations. So what I basically sketched here is the different aspects that you would have if you either do active measurements, passive monitoring, or you try to combine different crowdsourcing approaches. This is maybe also meant as a teaser for you, especially when you compare active and passive monitorings. There are some things you can do easily in active monitoring. There are some things you can do easily in passive monitoring. It might be very difficult for you if you want to turn that around. What I, for example, mean is active measurements are very easy if you do a voice call here and you want to measure voice quality. Very simple. You do it actively, very nice. If you want to measure average voice quality in a network, it's already pretty difficult if you do it actively, because you would need drive tests. You're not everywhere at any time, or you're not omnipresent, let's put it like that. So you would try to do that passively. However, what is the problem of passive monitoring? It's basically the opposite problem. You don't get results in the night. So if you use a passive monitoring system, or if you take passive traces, you have no clue what's happening in your network when in the night there's basically no traffic going on. So just as an idea, if you try to set up your experiments, consider basic ideas like that, and also consider actually combining them, for example. So there's a lot of ideas how to combine hybrid informations in that way. So I jump this. I promised you to present some of the results at least. First result was the idea to measure delay. Okay, let's assume we have a network like this. So UMTS network or an LTE network in that case, and we would like to measure the delay from here to here. So we would basically try to measure the different interfaces, and we would be interested to see the delay from each interface to the next. How would it basically look like? Well, if you would start off with a very simple approach and you analyze our delay in, let's say, HSPA, we have on the left empirical CDF basically with the round trip times. What are the different curves? Well, the solid lines are the IP connected base stations. The dashed lines are now the ATM connected base stations. You already see this is only the difference in the transport layer protocol. Yeah? So these were basically recorded. We took all the base stations in Vienna and we recorded a delay from different base stations at different situations for interface-to-interface information. So you see already, this is only the impact in the transport layer. This would be the difference that you have from a TTI. So if you go from 2 milliseconds to 10 milliseconds TTI, this would be the jump that you get from roughly 25 to roughly 40, let's say 2 milliseconds of time. So this is a bonus or an additional time that you receive. What is maybe a bit more interesting, let's jump to the other picture, is how these would distribute over the different elements. So if we would look here, we see downlink and uplink. So uplink would be the upper part, downlink would be the lower part, and we colored basically the different TTIs. If you look at the yellow part, that's maybe a bit surprising, but this is the time the data stuck in the user equipment. So the time when a packet goes into the device until it's transmitted on the air interface. The green part would be the synchronization time of the TTI. So you have to assume when you send a packet that is not synchronized, you need a certain time to fall into these brackets of the TTI itself. And finally, we have the processing time in the node B, which was still pretty large, and the core network itself. And if you look at that picture, you also understand immediately why one of the first steps was to reduce the TTI from 10 to 2 milliseconds, and now you squeeze in from 2 basically to 1 millisecond for these IP layer transmissions. So that is basically the first gain that you receive in these. Now you are ready for a bit more interesting picture. Let's put it like that. Or pictures, so to speak. There are 2 main pictures on the left side. On the left side is depicted the packet size over the one-way delay. So basically what you have seen before, the delay, one way, for packet size, different packet sizes. So if we go here, the packet was 500 bytes in size. If you go here, it was 1,000 bytes in size. 2 also different packet spacings. So how much time was there between a packet? The size is the size of the packet. The time between is the time for the beginning and the end of the packets itself. If you combine these two, then you have a data rate, basically. So if you say you send at a certain time with a certain size, you get a data rate transmission. What you see here is basically if a packet fits into a radio resource that you were assigned to, or if it does not fit. So basically, here you have a certain delay. If you exceed a certain size, you get a bit more time. So we jump from 30 to 40 milliseconds. What you see in this case, basically, is that even for small changes of packet size, you start to get more and more, let's say, delay each time an iteration. So obviously you get physical resources booked element by element, and then you have basically a constant delay for different sizes. So you get enough dedicated channel to fulfill a complete packet. Just remember the problem before where we said we had dedicated and random access channels. In the dedicated, you are capable to transmit more information to that. How would that now map to? If you combine these and these elements to something like that, you would have the arrival of packets and you would have the packet size. And you would, if you take basically the average over these areas, you would see that you have different areas with different timings or different round-trip times, one-way delays. So you have a sweet spot here, which obviously corresponds to a high data rate. So you have 27 milliseconds here. You have, let's say, a not-so-sweet spot here, where your packet size is too large to fit in one element. We have this jump, where we go up to 42 milliseconds. And you have then, here on the right, the low data rate sections, where we are not sending so many packets, where we immediately have a higher round-trip time. The most extreme case is we are sending large packets at a low data rate, 1 second. How can you try that? Well, try a ping. Try a ping and change the ping payload size slowly up from here to here. You will immediately see how you, even in that small experiment, suddenly increase these times. What is the problem of that? Well, this part you have maybe already experienced when you do a telnet session or an SSH session. So if you are interactive but at a low data rate and a few packets per, let's say, second or shortly below sub-seconds, you will experience quite a lot of delay by these kind of structures. Yeah? So this kind of structure will fall here, while this kind of structure will fall here, which corresponds to these elements here. Yeah? On the other hand, this is typically what you receive in the streaming cases. And now you also understand why there is a lot of optimization going on trying to rearrange these elements depending on your traffic itself. Because that what I'm showing you here is basically when you apply no quality of service rules at all, and you just run this test for different, basically data rates, at a normal mobile network itself. So you will experience a lot of different delay elements, or kind of reactive networks, as my colleague called that back then. Yeah, this was just a very short summary on these elements. Just to repeat again, or to let's say rub it in a bit, the mobile core networks act as a mobility anchor, also as a data anchor in terms of your IP address, and they assign you different qualities depending on your user profiles for the different data flows. We split it into an access and a non-access stratum, parts where we can access, parts which we see, like here, passively acting with our data. And we have basically distributed entities also that treat our network, or that react based on the network that we are injecting into them. Yeah? So be always aware that the network or the traffic that you offer will trigger a certain reaction of your network. And this is also getting more and more true if you do Wi-Fi measurements. And if you go for a bit more modern Wi-Fi hotspots, you will see actually a very similar behavior like these. This is actually also to explain you the preloading or elements like this was nothing else than you will end up in this section, and the ping test that you will directly do after will have a certain delay that corresponds to these, let's say 20, 25 milliseconds, but not in this area in that case. What are the other modifications? Well, one of the first modifications is M2M, so machine type communication starting with release 10 and 11. Target of machine type communications was basically to make the communication, let's say, for devices that have kind of automatic transmission of data, so non-human controlled and small data that is transmitted, more suitable for mobile networks. We have discussed before that actually we have a lot of overhead. We have protocol overhead, we have signaling overhead, and all that is happening. And if your other point is like a temperature sensor which sends, I don't know, 20 bytes an hour, then this is pretty much an overkill. An overkill in such a sense that if you monitor a mobile network nowadays, or let's say last year we did, the amount of signaling packets is basically identical with the amount of data packets. Let's say the number is the same. The volume is obviously not the same because data packets tend to be much larger, but you see as much signaling packets as you see data packets in a mobile network. So you would try to put down these efforts here. So the concept was basically that you come up with the possibility that you define a machine type user and a machine type server. So basically you would allow to have specialized interaction between a bunch of sensors that might be co-located, for example, and a bunch of servers that can enrich informations on the way. Huh? One of the examples, we basically, just to give you an idea of what you can try, we basically set up a scenario, or we basically performed this experiment. We did an autopilot scenario where we had a certain setup. We said, okay, we have certain cars that are traveling on the highway along, each of the cars will be communicating information, either updates or basically warning messages, and these messages are then processed in the back end. Okay? The question was, on one hand, how large gets the load in the network itself? So what is the excess delay that you can receive? And what is the load that you create by these devices? What we basically implemented, okay, that's a bit small, was something like that. So a very simple either periodic update or a burst in data rate transmissions. And okay, there's a slide missing. Okay, well, I will tell you first. I'm looking. Okay, then I have to tell you. There should be a slide with a result plot where you see we tested 10 different cars scenarios. So we basically tested between 1 and 50 cars. And depending on the car load, you see a severe drop in the cell performance. And you see the cell drop for non-machine type communication. And if you use the machine type communications and the corresponding configurations, you see that the performance will not drop in that extent. And that extent was that the call drop ratio went up by 30% for already 10 cars present in one cell, and went up to 60% if 50 cars were in the cell. So basically the cell was not accessible anymore for normal users trying to do voice calls in that case. Yeah, I'm sorry, I will update that slide or like send you the presentation for that. I don't know where that went in that case. Anyway, that was originally the intention or motivation to go for the IoT part of LTE, which is the direction where we are trying to, or where it's tried, that LTE gets more suitable for IoT devices. So basically, M2M should get more affordable in these directions. So what we try is, basically we have up to 4G, we optimized always one system. Now we would split into something that has more data rate and something that has more capabilities for the Internet of Things. Why is that a split? Well, if you go for the different categories, and that is basically saying if you go from one category to the next, you typically have improved the data rate, but you actually never went the other way, that you reduce data rate. Yeah? And if you go here for the categories 1 or 0, you go basically down to 10 megabits per second. Or if you go for the category M1, or even more extreme than this narrowband IoT, then you go down to tens of kbits per second, and you go into very small bandwidth technologies. The idea behind that is that you try to cut down the efficiency of 5G in such a way that you're able to have very deep indoor penetrations. So you hope that you reach your smart meterings, and you hope that you can serve all these base stations in that way, or basically all these elements in these L cases. Now I got a bit lost, I think. Anyway. I'm terribly sorry. I have mixed up my slides, I think, on the USB stick. Anyway, so let's try to do the best out of that. So basically, we talked about two flavors. We talked about a category which was the category M1 that is still capable of transmitting and streaming data, which is like 1 Mbit per second, so that would be optimized for any kind of video surveillance, control surveillances, or where you need a constant data flow. The next more extreme case was the narrowband IoT, where you're just capable of transmitting information, and you will only be delay tolerant at the cost or at the benefit of very low power consumption, but at the cost of a very low data rate possible in this case. No, that would be more the thing that I was doing. Another target is to reduce complexity. So you would try to limit everything in terms, this is why I said backwards in the category, and I was expecting actually the overview. that we go back in the amounts of modulation schemes that we allow, we go back in the bandwidth that we allow, and we actually go also back in the types of signaling that we allow. So before that, we had actually an overview of which protocols terminate where, and this is not the case anymore for these IoT elements. We have only reduced protocols that we can run in this case, or in that. Yeah, this was actually what I was looking for. What is the major change? And this is actually the part I wanted to target at. So far, we have never changed the signaling part in LTE or in any kind of mobile network. When you remember before, I said user equipment is attaching to a network, and we always assumed, well, the node will answer to the device itself. And if the device is asking for the mobile device to answer a call, we have said the protocol is supporting that this device is answering the call. So there's always a one-to-one relation, and a signaling is not just terminated or basically overloaded or elements like that. However, it's also clear that if the device has to communicate with the base station every 15 minutes or every half an hour, we are using a lot of power. And this is actually what we don't want to spend. So one of the first motivations is to get the power or the power consumptions down. So what you can do is you can remove the paging, for example. So you can basically say that the device does not need to answer to every paging. So you can say, I'm extending that and saying the device is online after a certain sleep time. So we can say that we disconnect the device for, let's say, 24 hours, and it will be online at a certain period of time where it can receive a data packet, or where it can be called for information. So this is basically where we say we allow a power save mode, or we allow a discontinuous receive information. Both of these features are a first indication that you see that these strict signaling protocols that we have, or that we have basically went through now, are evolving or actually pretty much changing. Not only in this consensus that we say there is no regular time grid anymore, that the device is called for, hey, please do a routing area update, and only the devices that call back and say I'm here are still considered to be connected, but also in the direction that we start to put quality of service, so to speak, on signaling messages. So if the MME itself is requested by a device to do a attach message or to process a signaling message, it has the capability to reject a certain amount of devices. So we can actually have an overload control also for signaling messages itself. Okay? That is, for me, the first takeaway message from this Internet of Things, the narrowband IoT LTE, because the idea to disconnect signaling from, let's say, to be mandatory changes also a lot when you perform, let's say, data rate tests or availability tests or performance tests. So this is actually what we are currently doing. How do you now prove that a device has a certain reachability? So now you have a new system, you are indoor, you can do deep indoor penetrations, you have a smart meter, but how do you test how to reach the smart meter now? Because you don't have only the component of the data flow, you also have to consider that the signaling itself does not need to be one-to-one. So you basically have to adapt that you first measure the availability and the connectivity of the device, and then you have to measure basically the data availability of the device itself. So these are the two main components in this direction for me. Yeah? Sorry.
What was the key for extended reception? You said that these
Here.
things were actually changing, but from your words and from what I read there, I actually
Extended.
see an extension to say
Mhm.
that we are going to
Yeah, but
make it even bigger the time that you are waiting to use this.
but you would not be able to do it nowadays, because if there's a routing area update from the base station and you're not present, you're just deleted from the network. So all this mobility management, there was always an implicit detach. So if the network doesn't hear you, you are deleted. This is how the network basically kept itself sane, so to speak. So users that take out their battery or so, or don't detach from the network properly, are deleted in the system.
So the change is that you are adding something on the core network side.
The change is that you actually accept these things to happen or to be flexible. Because before that, implicitly, you always assume that they are strictly existing. So if you do, after 15 minutes, an update, and you basically ask the whole cell who is here, and the person doesn't answer, he gets deleted. And these basic concepts now lead to actually a much more or much bigger mobility management state diagram. Because you basically have to say, okay, I have to check a configuration parameter, and I have to have a mobility management that is different for different devices. And this was the point, so you have to now, before that you could assume every device is treated the same, so I don't have to consider it, because if I check outages or so, I would check on the data plane. But now I have also to consider the second element of the mobility management, and I have to consider it for every device, like on its own, to understand if it was implicitly detached, or if it's really not reachable, or something like that. So the analysis part is not anymore on the data itself, but needs to consider that all these now gets flexible. So the point is, yes, that looks like a very simple, small change, but actually it has this huge impact everywhere else, because you always assume that this exists, that there is, the list that you have is up to date. The devices that call back are the ones that are present, and things like that.
Where do you think that there's some source of information where we can check that? Because these ideas, they seem simple.
Yeah.
But now I understand the change, but they still seem simple.
No, this is...
Not complicated, but for example, we have one of the PhD students
Yeah.
directly with this.
This is like... Yeah, no, I mean, this is what I basically borrowed from Qualcomm. This is like Qualcomm's report on narrowband IoT. But I don't think it is really finally standardized. Yeah? This is what they think is their idea. And they also don't talk about what that means for the core network. So if you read actually that presentation and the white paper they have, they never actually talk about what that means for the rest of the world, or the rest of the LTE environment. But it basically means that this MME and whatever, they have to keep track suddenly of days of, or let's say at least much more devices than they had before. And it might also be more complex, because if you imagine that it's on a container that doesn't need to wake up in the same cell. It could wake up, well, 40 minutes later somewhere on the other side of the city, and things like that. So I think that will not be that simple. I mean, this is simple, yes, but if you do that, I think it will have a very big impact on the others. This is why it was the slide I was looking for, because, yeah, that was the, yeah, sorry.
I have a question, it might be a silly question, but I mean, how does the base station, then push data to the device? If it wants to push some data to the device,
Mm-hmm.
if it's sleeping, then is there some way to wake it up?
No, the idea here was that you say how long you will sleep. So basically, this is what I meant with the configuration. So the device can, as a configuration, now say, instead of 2 seconds or 15 minutes, I am sleeping for 24 hours or for 40 minutes, and then you know when to reach the device again. But it's exactly what you say. Before, the base station was assuming if I trigger something on the paging channel, the device will come online. And if it doesn't come online, it's not here. But now, basically, you have to wait to the right time spot, call for it. And they actually have also that they say you have to call it at least 3 times until you are sure that you have reached it, because they want to have deep window penetrations and elements like that. But that actually changes completely the this idea of that we had before. You have a paging channel, you call it the paging channel, and either you wake up or I have turned it off.
So it has to be device dependent. I mean,
It's a configuration.
depend on the
Yeah.
configuration will
So you-
depend on the device.
You basically need to keep a new idea of this.
If
but-
it's very sporadic data, then you know.
Yeah. I mean that is
device, then it can see
that is
for long.
basically the goal. Yeah. So the idea here. I mean there are a lot of these other elements, but as said, I don't think. I mean I see it always from the eyes as a person who did passive monitoring quite a lot. That will be interesting then. Let's put it like that. But as an idea, this is why I basically looked into what was on the homepage, what you do, and this is why I pushed it a bit in to give you a teaser on that, and that you can follow these standardization parts also, because they're in the newer releases. But yeah, what I wanted to give you as my part of the message was that you have to consider, and this is why I was also pushing all these protocols and procedures, that they will not stay untouched, because a lot of the assumptions you do there, might need updates. Let's put it like that, just as an idea. Okay. You. Did you?
I was going to say something, but I think it's still related to this, but it's more like it's more of a comment.
Feel free. No,
No, I was thinking about another possibility. Now it's coming into my mind. Because one of the I used to work on problems. One of the problems I saw once was when you have discontinuous reception on in situations where your radio conditions are not good, your percentage of drop calls increases quite fast.
Yeah.
Why? In a mobility scenario, you are moving outside towards the cell edge. Your radio condition enough. You don't need to go to the
Yeah.
cell edge, but your radio is going down, and you are sending DPC
yeah.
bits to say power up, power down to the EV. And as you have discontinuous reception, you are not using the whole time that you have available. So the information to power up or to power, in most cases it will be power up, doesn't get to the terminal on
Yes.
time. And then it doesn't know that it needs to power off.
And it's gone.
And to power up, and the call drops. So it might be interesting also in the smart city scenario. It might be interesting as well to look at the radio conditions.
Yeah.
And what you can do, what you could add.
No.
But is more of a comment.
Yeah. I mean, no, thank you very much for the comment. I mean, we had what I was also observing here, or what I was reminded of, is when we did passive monitoring, we discovered a lot of cells with very high drop rates for voice call and everything. And it turned out that these were cells along highways or along train tracks. And when a train changes between two routing areas, you have hundreds of phones that are suddenly in a new routing area. And you don't have enough signaling channels. Yeah? We discussed it, there are dedicated signaling channels, and if they're full, they're full. So it took like 3 cells until everyone was reconnected. If you now map that to this scenario and you take a container ship that, I don't know, arrives somewhere in a harbor, it will take days until they go online again. I mean, hopefully they're still there or whatever, but I think this is not thought to the end yet, because exactly this application where you need to do that will be harmed quite a lot by all these scenarios. A lot of sensors in one place that wake up at the same time or start to iterate on these. So I'm not really sure if it's worth the pain that this will create to implement that. What you might have to understand, I skipped that a bit, but this narrowband IoT is a very political thing, because there are these other technologies like LoRa and other low power technologies, and 5G or 3GPP is desperately trying to catch up. Yeah, so they just pushed it in, so to speak. So it doesn't need that this is really the thing that will fly, but obviously, I mean, Qualcomm and others have licenses, and therefore they're pushing hard for making this to happen. So this is more also this is why in the slides you will read, if you read from Qualcomm, that they have security and that you can use one SIM card and all the benefits the 3GPP network will have, but not really about this. This is why I said take it with a grain of salt, so to speak, rather than to just follow up on it, basically. Yeah, time has progressed, so yeah, this is just how you can use it in FDD or TDD, basically. And I think, did I not? Okay, I did not include that here. Okay, no. I just summarize it up because the time is pretty far. So the narrowband IoT is, this is why I wrote that it's a piece of the solution and connectivity is a piece of the solution, but just forcing it like that and putting it into a system that would use different ways is, well, one kind of thing. 3GPP hopes that they can offer both streaming and messaging. Streaming would be this category M1. Messaging would be the narrowband and narrowband IoT. Don't be really fooled. Just because it's called narrowband IoT doesn't mean it has a lot to do with LTE. It's 200 kilohertz bandwidth, different kind of modulation strategies and different kind of deployment strategies. So it is, the physical layer is severely different. And also, as said, understand that this has quite some impact on the signaling and the other layers that have to be dealt with in this case. What it can show, but I mean this is by definition, is that you have a low complexity. Well, you sacrifice a lot of bandwidth. You sacrifice that you are full duplex. You're just half duplex. You sacrifice that you can use higher order modulation schemes. And you then have the long sleeping times, which obviously will lead to a higher battery life in that case. What might be more interesting is to look at 5G. And this is why I wanted to put on the first part of this 5G presentation, because in 5G you're much more flexible in the modulation and coding, and you are also more flexible in the way how to select your modulation format. Yeah? You can go for either in frequency or in time, more discrete, and therefore you can also be flexible in assigning resources to different users. So that might be also more of interest for you. Yeah, this was just as a take-home message, and to be aware of the access and the non-access stratum, so that there are parts you see and there are parts that might mess up your data traffic without seeing it. Be also aware that you share these interfaces and these procedures. As said, the train that moves through cells over a routing area and then blocks all the other users. The other users don't have bad receptions. It's just that the network itself was busy with the activities. The network is typically reactive to your traffic. So if you do any kind of traffic monitoring, if you try to do traffic measurements, be aware that it will take several different states, and it will react to what you offer as a data rate. And therefore, some metrics make no sense per se, but you have to define your own matrices, like delay as packet size or data rate. There might be other side effects, like that you preloaded your measurements, or you have too large packet sizes, or your spacing is not accordingly, or any elements like this. And yeah, there are 5 minutes left, so I can charge you with the homework. No. I would ask you, if you're interested, to provide you two kinds of homeworks. The first homework would be a simple one. You can directly find it on the slides. The first thing is that you try to play around with the ping times and that you explain the differences. The second part would be that you can also select something else. Assume a certain state, a certain network, and you assume that one of the nodes is failing. Yeah? So for example, an MME node is rebooting. What is happening next? So they would be just to tease a bit your brains. Yeah? There's no right or wrong. It's just to that you think what happens if this entity goes down? Which features are not available anymore? Will the users drop? Are they able to still transmit data? What will happen after 15 minutes? What could happen if a new user tries to connect? Is maybe the easiest, doesn't work at all. Or what will happen to the user experience? You can also feel free to delete any other node. This was just the simplest node. This can happen. I'm just saying from passive monitoring, you see that happens. But yeah, in that way. And the last one is either you can simulate it, any simulation tool you try, or you can do a practical measurement. I don't know what you do more, applied or more simulations, to analyze what happens to a TCP flow that you transmit in a mobile network. Look at the round trip times, the window sizes, how long, what will happen to the packets itself, what happens to the inter-packet spacing. Some will be back-to-back, some will be stretched, for example, depending on TTIs, depending on the resources you have booked. So you will see a lot of effects that come in there. What do you notice if the flow is short or long? Typically, there might be a difference in that. You can also, if you're more experimentative and you're happy to drive around, can do some handover tests in that case and analyze the TCP flow. That would be just to, if you can answer these 3 questions, I would say everything perfect. You don't need to open any book or any standardization anymore. Most of that is somehow solved. And the last homework would be for anyone who is then still interested to write me an email. I have actually prepared 2 traces, not really recorded from a mobile network, which are 2 performance traces you would receive. You ask 2 network operators to test performance of the users, and these would be the 2 traces that you receive. And the question or the answer is easy. That we look for is which network is better, because that's always the answer, and all the rest would be up to you. So you have to decide what is the metric that I say it's better. Is it the delay? Is it the round trip time or the throughput? Was there maybe a difference in the testing methodology or elements like these? So that would be the idea for my second homework if you're interested. Yeah, I would be happy if you find the time and the interest. I don't know, have you worked with Wireshark, or who has worked with Wireshark already? Okay. Well, then I will prepare it also as a time series. Let's make an alternative. I will do a time series out of that. So you are free to use anything like MATLAB or so don't be afraid of Wireshark. You don't have to do. No, actually, if you're interested to do something like that, I warmly would ask you to use Wireshark, because it is really, really powerful, and it can already decode a lot of mobile protocols. It's really amazing. You put in a lot of traces, and it is able to decode most of this on the fly. So it's really nice in that way. But I will not force you. I will, if you ask, you get a time series. No, I will just provide you as a time series if you want. And that is just my idea to tease you a bit and to check your own knowledge. And so to answer these, let's say, toy questions, and maybe to answer the ideas of a toy trace as a final idea, not as an exam, please. Just as an offer in this way. Okay, so thank you for your time, and see you soon.
Thank you.
Other questions? Or do we? I have to admit that I will not be long around. In fact, I have to rush soon. So I can just encourage you even further to ask me any email questions or anything in that direction. Yeah, you have a question.
Just a thing that, are you familiar with the recursive internetwork architecture?
No, I don't think so.
I think I just came across it when studying Professor John Day actually introduced it. He's in Boston University. And it's basically he suggested an
Mhm.
which basically supports mobility and multi-homing and multicasting pretty
Mhm.
inherently. I mean, it makes it very, elegant.
Yeah.
Right. So I was just thinking if can have some thoughts of yours, but okay.
No, I have to admit, not really, in that way. Actually, we studied it a bit like 2 years ago. I don't remember that we studied this one, because of the challenge that if you consider that you have different paths for your data flows, it gets even more interesting to understand what is the performance that an end user reaches. And it's also the question, how would you assign different packets, for example, or different elements of this to an end user. It's actually something that is coming back with Wi-Fi offloading, more or less, and also with as soon as you share two links with different qualities, and especially if they are varying, so they are going up and down quite a lot, then the question how you assign packets to different elements is an interesting one. But yeah,
I think
not
the
really
main
more than
idea
that.
in that is that it introduces a new model for computer communications,
Mm-hmm.
which is basically like it uses the model for distributed computation for
Yeah.
communications.
Mm-hmm.
That it's basically an inter-process communication between
Yeah.
and these processes may be mobile
Mm-hmm.
amongst. So it analyzes different methods of naming and addressing of devices.
Mm-hmm.
So which inherently claimed to be more suited to mobility. So I was thinking
Okay.
that if something
Mhm.
was being done in 5G or in terms of
No, not really.
yeah.
No. Not really.
I'll
Like.
send you a mail.
Yeah, please.
Just send you some links.
Sounds interesting, for sure. Okay, then have a nice evening. Enjoy London. Don't freeze. See you soon.